Next, I want to do some applications here. So one thing is with slope is we can also think of slope as a rate of change. So we use this idea a lot in application problems, where instead of thinking of it more as like a vertical to horizontal change, which it still is, we just think of it as like a change overall, like an average change overall. So it can also be interpreted as a rate of change. And let's look at an example here. So the line graph on the left here shows the percentage of American men and women ages 20 to 24 who were married from 1970 through 2010. Okay, so in the blue line here, you have women, and in the red line here, you have men. And again, these are people who are between 20 and 24. And over here, you have the percent who are married. So just overall, before I read any further, you can see that, back in 1970, about 45% of men were married in this age group, and about 65% of women were married in this age group. Whereas in 2010, those percents dropped to 11 and 21 substantially. So people are just getting married later. This is a pretty early age group from 20 to 24. So we're just looking at that change in, kind of when do people get married. We want to find the slope of the line representing the women. So we're going to focus on the blue line here, and then describe what it represents. Now, I started with a solution. I haven't done the full piece out yet, but we're going to let X represent the year, and we're going to let Y represent the percent of married women. And there are 2 points that are clearly shown on the graph. So you just want to make sure that you use points that are clear that you can find. If I have 2 points that are clearly given, I'm not going to try to find anything else in between. So use the ones you have. With slope, it doesn't matter which 2 points you use, you'll still get the same answer. So my first point is 1970, 65, and then 2010, 21. So for my slope here, I'm just going to let this be the first point and this be the second point. I have 21 minus 65, and then I have 2010 minus 1970. In the numerator, when I subtract, I get negative 44, and in the denominator, I get 40. Now, we're going to simplify this here. So one thing we could do is we could just divide both of these by 4, right, to keep it in a nice fraction form here. So you have negative 11 over 10. Sometimes with rates, we will use the decimal version as well. So your book likes negative 1.1 here. I would say most times with slope, we do tend to leave the fraction form unless it's an applied problem, where then we may switch to the decimal form instead. Now notice the slope is negative, which makes sense because that line is decreasing overall. So it's just kind of a nice check to make sure we haven't made an obvious mistake. Doesn't mean doesn't check all the details, but at least we know we're going in the right direction. So here's our slope here. So that answers the first part, to find the slope of the line segment. And then we also need to describe what it represents. So I like to think about my units here just, before I start describing anything. So remember your numerator is your change in Y's, and our Y values are about the percentages, right? So the top part is about the percent who are married. And then the bottom here represents the year, right? So we're really comparing the percent who are married versus the year. And our rate of change is negative 1.1. So what this is saying to us, and one thing to note here, if you don't have a denominator, there is always a 1 there. So when we're thinking about rate of change, this is going to be the percent change for 1 year. Because again, if there's no denominator, there is a 1, and our units in the bottom are years. Our units in the top are about the percent. So what's actually we're comparing here is how the percent is changing compared to the years. So what this means is that about each year, the rate of women who are married, and again, this is from ages 20 to 24, decreases by 1.1%. Or you could say changes by negative 1.1% as well. That works too. So if I use the word decrease, then I don't need to put the negative in, right? Because decrease implies that it's going down. If you don't like that, what you could say is the rate of change is negative 1.1% per year. So you could say that too. So there's different ways that you could write this sentence. All right, let's do one more application. Oops. Okay. All right. So modeling data with slope-intercept form of the equation of the line. So the slope-intercept form of the line is useful for obtaining mathematical models for data that fall on or near a line. So when we have real-world data, it's not usually perfect. It will likely never fall exactly on a line, but there is a lot of data that does fall very close to a line. So we often will use a linear equation there to model that real-world data. And you have the example here. So in this case, we're looking at the average age of a person's first marriage in the United States. Here, blue is women and men is in red, and the same thing here. So in 1970, the average age of a woman's first marriage was 20.8 years old, and for a man was 23.2. In 2015, the average age of a woman's first marriage was 27.1, and for a man was 29.2. So again, you can see that change over time, that people are just getting married later. And then you have that same information here, although it's just given in a different format. So looking at like a time series graph instead, a line graph instead of having a bar graph. So in example 8, we're going to show how we can use that equation y equals mx plus b to obtain a model for the data. And then using that model, we can make predictions about what might occur in the future. So for part A, we're going to use the 2 points for women from figure 7.26b, so I guess we're using this one, to find the function in the form w of x equals mx plus b. So we're just using w for women instead of y here. That models the average age of first marriage for US women, where x is years after 1970. So just be careful. We're talking about years after 1970. So when x is equal to 0, that means in 1970. When x is equal to 1, you're 1971, and so on. So the points that we have here are 0 and 20.8, and then also 45 and 27.1. So I'm just getting those right off my graph. And again, that 0 is in 1970, right? And then that 45 would be in 2015. So we're talking about years since. So the first thing I'm going to do is find the slope. So I have 27.1 minus 20.8. So I'm subtracting my y values here in the numerator, and then I'm going to subtract my x values in the denominator. And let me just check my notes here. So what I get is 0.14. Now again, a lot of times with slope, we do leave the fraction, but where our data is already in decimals, it makes sense to change that over to the decimal notation instead. So I'm going to leave my slope as 0.14 here. And I'm going to come back to the W notation in a second, but when we write an equation of a line, we're trying to be in this form here, like this y equals mx plus b form, right? So in order to do that, you do need a slope and you do need a b value. So I do have my slope here, right? I found my slope was 0.14. So I need the b. And remember, your b is your y-intercept. So if I look back on my graph here, my y-intercept for women is this point right here, right? Isn't that where it crosses the y-axis? So my y-intercept is that 20.8. Your y-intercept always has an x value of 0. So we can pick that right out here, and it's 20.8. So my equation is y equals 0.14x plus 20.8. And we are using function notation. They want us to use w for women. So I'm just going to change this y over to the function notation instead. Notice my slope is positive and my line is increasing. So again, we're going in the right direction there, which is good. All right, now we're going to use the model to project the average age of first marriage in the US women in 2030. So first of all, we have to be careful. So we're looking at 2030, and remember, we're starting in the year 1970. So if I subtract these, I'm looking at a change of 60 years. Oops, can't see that, 60 years. So my x value here is going to be 60. So I'm going to take my function, I'm going to plug in 60. Anytime I see an x, I'm just going to replace it with that 60. When I multiply this together, I get 8.4. And then when I add these together, I get 29.2. So we are going to project the average age to be 29.2 years old. Now, one thing I will kind of warn here when making predictions, which I think is kind of skipped over in this example, is that our data only goes up to 2015, and 2030 is pretty far away from that, so 15 years later. You know, we only have about 45 years of data here from 1970 to 2015. So I would just be a little bit cautious with our prediction because we're getting pretty far away from our ending data point. Normally we want to make predictions that are pretty close to the end of our data. So, you know, predicting something for 2020 seems very reasonable. Predicting something for 2030, I think we can do it, but we should, you know, take it with a grain of salt, meaning that understand that this is still 15 years away. A lot of things can change in 15 years, right? With patterns and social context here, right? So when people are actually getting married and so on. So I think this is a good starting prediction, but again, I would note that 2030 is pretty far away from our data. So it may not be exact. So as we get more data in the coming years, we may want to tweak our function so that it keeps getting more and more accurate. So that's it for linear functions, lots of applications. And again, there's lots more we can do with it too, so that you may have seen before. So we're just kind of focusing on the basics here, your graphing, your slope, and some of your applications. But I hope this was a good review for you, or if there's new material you haven't seen before yet, then it was good and you understood it. But if not, you know how to reach me. You can always send me an email.